Hi everyone and welcome to Build 2015. Today we're going to talk about how you can build faster and more powerful cloud-powered apps with the Windows 10 app platform. I'm Siddharth, I'm a program manager on the Windows Networking API team, and this is Himadri.
Hi.
He's also a member of our team, and our team basically builds all the APIs that your app needs to talk to the network and to the cloud. So let's start this talk by understanding what we mean by cloud-powered apps. So a cloud-powered app is really any app that fetches content either from the internet or from peer devices. So you can think of these apps as your news app, your sports score apps, or even things like a peer-to-peer chat or a peer-to-peer game. And these are typically built using networking APIs that we provide in the Windows platform. For example, a peer-to-peer app would typically use sockets. If you wanted to talk to a web service in the cloud, you would typically use HTTP, and so on. Now, what do we mean by we are making it faster and more capable? So we are going to provide higher performance sockets APIs that will let you do much faster peer-to-peer communication. We are also providing faster HTTP, and this will help you improve the performance of your web services code. And finally, we are adding new capabilities to our background data transfer APIs. So in this talk, we'll go through these one by one, going up the stack. So we'll start with sockets, we'll then go over to HTTP, then we'll talk about background transfer, and finally we'll hit a summary of some of the other improvements we have in this area. So first, let's start with sockets. So you know that most apps will use sockets only when they're in the foreground, and that's because having sockets in the background is really expensive for the system. In Windows 10, we have taken a step to solve this problem. What you can now do is have your socket listening in the background even when your app is not running, and this enables really powerful scenarios. So let's look at what is happening. Your app would create a socket when it's in the foreground, and you would also associate it with a background task that you yourself have defined. Now when your app gets suspended, so when the user navigates away, you would transfer the ownership of that socket to a socket broker. A socket broker is basically the name of an OS component that's always alive and listening to sockets even when your app is not around. Now when there is activity on your socket, for example, it gets closed or it gets an incoming message, the socket broker detects that and it will launch the task that you had associated with the socket. The task can now access the socket, get ownership back, do stuff on the socket, and then return the ownership to the broker. Finally, when your foreground app is launched again or it resumes, you can get the ownership of the socket back and use it just like you were earlier. And the really cool part is when you get the ownership of the socket back, the data is still on the socket and the socket is still connected. So let's look at some code samples. Let me use a pen. So you would basically define a trigger that's a socket activity trigger. And this is a new class that we are defining in Windows 10. You would then build a background task that subscribes to this trigger. Now when you create your socket, you also enable transfer ownership on that socket. This basically tells the system that, hey, you can let the ownership of my socket go from the foreground app to the broker and to this background task that's named as task. Finally, you would, of course, connect your socket to the remote endpoint. Now, when your app is being suspended, we are familiar with the onSuspending method that gets called when an app is being suspended. You would basically define a socket ID, which is a simple string, and you would then cancel all the pending I/O operations on the socket. Now, this step is really important because if there are pending I/O operations, the ownership transfer to the socket broker will fail. So you really need to cancel all the pending I/Os and then transfer ownership to the socket broker. So now at this point, your app is suspended and the socket broker has ownership of your socket. Now assuming there is some activity on the socket, your background task gets launched. So this is the code you would write in the background task. You would basically access the trigger details from the socket activity trigger, and then the socket information object in the details will tell you the reason why your background task got triggered. So it could be that there was activity on the socket, it could be that a keep alive timer expired, and so on. And in your background task, you would have to handle each of these cases separately. Now it's really important to note that after you have handled the case, you need to transfer the ownership back to the broker. And this is important because when your app gets resumed, it wants to find the socket with the broker so it can get ownership back. So here's how you do that in code. Once your foreground app resumes, you basically access this static API socket activity information with the socket ID that you had defined earlier. This basically tells the socket broker that, hey, out of all the sockets that you have ownership of, give me back the socket that has my socket ID. And then again, once you get this socket, it's already connected, it already has the data on it for you to read, and you're good to go. So that was about the socket broker and how you can run sockets in the background starting Windows 10. So we hope that this will enable many cool scenarios, especially for peer-to-peer chat or incoming call notification kind of apps. Next, let's look at a new low overhead path that we have enabled for bursty sockets. So when we look at the write async operation on a socket, which is when you're sending data out, each write incurs a transition to kernel mode code and back into user mode. And this sort of creates a lot of overhead in that write path, and that's why apps such as VPN apps or VoIP apps that have many such data buffers being passed out incur a lot of overhead because of this. Now in Windows 10, we have enabled a new pattern that optimizes this frequency of kernel transitions. Let's see how we do that. So if you're a beginner programmer, or if networking is not really the focus of your app, if you just wanted to write a few data packets out on the socket, you would presumably use a pattern like this. You would have a list of buffers that are the packets that you want to send out. You would create an output stream, and then for each of your packets, you would simply do a write async. And this is simple and easy to debug. It does the job, and you can send the data out. However, as we noted earlier, this leads to a kernel transition and back for each of your write operations, and hence you suffer in performance. A higher performance pattern that exists even back in Windows 8.1 is that you can create an array of your tasks, and then for each of your packet, you basically track the write operation as a task, but don't wait for the previous one to complete before issuing the next one. That way, let's say you have 100 packets, you could just issue all the 100 writes and then wait on all of them at once. And this pattern really helps us in the operating system to manage your packet buffers and do the kernel transitions in an optimal way. So this pattern we have made even more efficient in Windows 10. We'll soon see a demo of how fast that is in Windows 10. But note that this pattern only exists for C# developers because it uses tasks. Now, there's yet another pattern that we have enabled in Windows 10, which is using the operation of flush async. So essentially, you're doing a very similar kind of pattern. You're creating all your write operations, but instead of using a task, you use an async operation with progress. Now again, you have this array of buffers. You simply issue all the writes, and then finally you call flush async. Now the behavior of flush async API has changed from Windows 8 or 8.1 to Windows 10. In Windows 8.1, flush async would return to you immediately and not guarantee that all your writes have completed. Whereas in Windows 10, the behavior has changed to guarantee that all your writes have completed. And then you can look at whether the status was a success or a failure. So these two patterns, the task.waitAll and flush async, really enable a much faster performance on sockets. Some important considerations to note though is that once you have issued all the writes, you should be careful not to modify the buffers until all the write operations have completed, because you should sort of think of the operating system as having ownership of that buffer for that while. And as I mentioned, the flush async pattern only works in Windows 10 onwards, and it only works for certain classes of sockets. So it only works for stream socket and for a connected datagram socket. Of course, for either previous versions of Windows or for other types of sockets, you can continue to use the tasks.waitAll pattern. So now let's quickly jump into a demo and see how much faster. So here I have an app that basically compares the sending speed with the batch sends and without the sends. And you can of course set the remote address and remote endpoint and so on. The data buffer size is configurable. So let's quickly start the demo, and we observe that the batch sends gets done much faster. In fact, it's 4 times as fast as without the batch sends. We can also see that even if we increase the data buffer size, which means we are now sending larger packets, it's still significantly faster than without the batch sends. So you clearly see how much faster the new pattern enables your code to be, and it really empowers VoIP and VPN apps to be much faster on Windows 10. So that was an overview of the improvements we are making in the Sockets API. Let's now move over a layer higher to HTTP and see what improvements we have for you. So you might be familiar with the windows.web.http API, which has been available since Windows and Windows Phone 8.1. This is essentially an API that we provide to implement the HTTP client role on your devices. It was designed very similar to the .NET API, which has been around for a little while longer, and this helps us minimize the learning curve for developers who are adopting this API. So the basic pattern is that you create a single client object, and then you can use it to issue multiple requests to multiple servers. You can also optionally customize an object called the HTTP base protocol filter. So you can think of the base protocol filter as being underneath the client and powering the HTTP communication. When you create a client, we create a filter underneath by default and give it to you. But you can optionally also customize the behavior of that filter. Further, you can just create your own filter and completely bypass the OS provided filter. And finally, you can chain multiple filters so that you can process a request as it's going out or a response as it's coming in. For more discussion on the chaining of multiple filters, I would point you to the windows.web.http.filters namespace documentation MSDN. It has a really good description of how you can do this chaining and what it's useful for. So the big news now is that the API of Windows Web HTTP gets HTTP2 support starting in Windows 10. So what is HTTP2? I'm sure a lot of you are familiar with this term, as it is the new evolving standard for HTTP and is the next version after HTTP 1.1. So essentially what HTTP2 does is that it multiplexes multiple streams or request response pairs in a single TCP connection. Now why is this faster? Using a single TCP connection means that you incur much fewer round trip time to set up a connection every time you need one. Also, there are fewer bytes being sent on the wire because HTTP2 uses what is called header compression to minimize the number of header bytes it's sending for every request. And finally, I would like to point out that HTTP2 is no longer something in the distant future and you can think about it later. It's really here. A lot of the big players on the web, Microsoft, Google, Facebook, Twitter, Akamai, are already starting to design their web services and upgrade them to HTTP2. So this is really something that's here, that's now, and we really need to start developing apps to take advantage of this. If you're more interested in HTTP2, there is another talk in Build by Rob Trace which discusses all of HTTP2 in Windows 10. So let's look at how we enable this in the API. The best part is it's on by default. So whether you have an existing app in the store or if you're writing a new UAP app, you get this for free without any code change. We have also built in negotiation. So if, let's say, the client talks HTTP2 to the server, but the server does not understand HTTP2, it's still HTTP 1.1, the client will automatically fall back to HTTP 1.1 and your app would never be affected. However, we do understand that there might be times when the HTTP2 version of the server has a bug or you are just trying to bring up both client and service endpoints, and you're still working through your debugging. So it's a single line of code change to explicitly switch back to HTTP 1.1. We'll soon see a code fragment of how to do that. And finally, we are also working on enabling HTTP 2 support in the .NET API, so that no matter which API you choose to write your UAP app, you would get HTTP 2 support built in. So let's quickly look at a code sample. As I mentioned before, there is the HTTP based protocol filter that essentially powers all of your HTTP communication. After you create that filter, there is a property called max version on that filter. And again, as I mentioned, the default value in Windows 10 is HTTP 2.0, but you can go ahead and set it to whatever value you like. Now, this max version basically says what the client prefers as the HTTP version. So now you create the new client object, you send a request to the server, and now when the server sends you back a response, you can query the version property of the response to understand right there. You can query the version property of the response to understand what protocol the server is using. And it's really important to note here that even if you specify HTTP 2.0 for the client preference, depending on the proxies that are between you and the server support itself, you may not really be talking HTTP 2.0. So let's quickly switch to a demo and see how this works. So here I have the app for HTTP 2.0. Let's go ahead and run it. So we see, like, for HTTP 1.1, we are in this app, we are basically downloading a set of thumbnail images from an Azure website. First, we'll use HTTP 1.1 and we'll see how much time it takes. So you'll notice how all the images are coming down in series. They're coming down one by one, and that's the typical nature of HTTP 1.1. If I switch to HTTP 2, it just comes down much faster. And I'm making sure not to cache any resources, so we can look at it again. If I download it again, it takes 2.3 seconds. Try HTTP 1 again. It takes much, much longer. Looking at the code, as I mentioned before, there's only this one line of change where you can simply switch between your max versions being HTTP 2.0 or HTTP 1.1, and that's it. You get HTTP 2.0 support in your app. We switch back to my. So that's all we had for the HTTP API. We are really looking forward to the great scenarios that developers enable with HTTP 2, and we would love to hear feedback on how we can improve the API even further to let you take advantage of HTTP 2. Next, Himadri will now go over the improvements in background transfer API.
Thanks, Sid. That was really exciting to see so many improvements in sockets and HTTP. Now, I'm sure all the developers are going to use those APIs and build interesting scenarios. But we haven't stopped there. We had moved ahead and also added bunch of new features in the Windows networking background transfer API. Background transfer, as you know, it is not a new API. This is from Windows 8, Windows 8.1 timeframe. The basic API pattern is very simple. You create a background downloader object, and you can schedule a bunch of background downloads or uploads using that downloader object, just passing on the URI and the file with it. The cool part is that this API is network resilient. Like if your Wi-Fi connection goes on and off, the transfers doesn't fail. They automatically resume and lets you download large content like music or video or podcast in the background. A lot of apps like OneDrive and music and video apps, podcast apps use this API to download their content. The other piece which is very interesting is the API has inbuilt intelligence in terms of how much data your cellular network has. What is your data plan, and it is data sense and battery sense aware. So we have taken a huge step forward and added a feature called post processing in the background transfer API. Now, what is post-processing? It's basically an ability to run your application code even when the user is not using your application at the end of your background transfer. So say you have a huge movie which you are downloading, and at the end of the download the app wants to do something which earlier it has to do only when the user is using the app. Now they can do it right at the end of the transfer, right at the end of the download. How do we do that? We are actually building upon the background task infrastructure, and I will delve a little bit more on that in the future slides. Okay. So what are the scenarios which background post-processing enables? One of the interesting thing which it enables is that it gives the app ability to run automatic processing of the downloaded files. Like after the download happened, you can process the file automatically. You don't have to wait for the user to come back to your application to process those files. A lot of times, a lot of apps have server-side transaction logic at the end of the download. Like you purchase the music download happens, and then you want to send an acknowledgement to the server to complete the transaction. Now it can be done right at the end of the download. You can also add customized failed transfer retries. Now background transfer does some amount of retries on your behalf, but if you want to have more control and do some more interesting things after the download has failed, you can do that using this feature. So let's look at what is the programming pattern. In Windows 8.1, the pattern was very simple. You create a background transfer, and then you have to start those transfers from your app. Once the transfers get started from your app, the background process takes over and transfers the data in the background for your app. And at the end, what it does is it sends a completion handler callback to your app. Right? Now, in Windows 10, what we have done is using three additional steps, you can add a support for background post-processing. The first step is after you create the background transfers, you can create a background task and a completion trigger, and then link the background task and the completion trigger to the transfer before starting the transfers. So in that case, what will happen is after the transfer is complete, the OS will take care of launching of your completion handler task at the end of the transfer in the background, and you also have an option to handle the completion in the foreground if your app is running. So that's pretty powerful. Now let's look at each of these three steps in a little bit more detail with code samples and how do you do that. So first step is to create a background task and a completion trigger. So for this, what we have done is we have introduced a new class called background transfer completion group. Now those people who are familiar with background transfer API might remember that there is something called background transfer group, but this is different from that because it gives a ability to batch a set of transfers after which a task should be run. So what we do is, in this case, we create a simple background transfer completion group. Then we, the usual background task APIs, we create the background task. But the interesting thing is that we have to set the trigger of the task to the completion group's trigger. So that's how you will create the task, create the completion group, and set the task's trigger to the completion group's trigger. The next step would be to link the background tasks to the transfers. Now for that, that's also a very simple piece of code. As usual, we usually create a downloader to add the transfers. Now in the background downloader constructor, you can pass on the completion group which it belongs. Then you add, as usual, all the download operation to the downloader, and at the end, after adding all the transfers, what you have to do is you have to say completion group dot enable. What it means is really a transaction commit kind of thing. So you are indicating the indicating that using after all these transfers are done, then only spawn the background task. So now, what do you write in the task code, right? Like when the task is launched in the background, how do you know which downloads have completed? For that, you need to just check on the background transfer completion groups triggers. The trigger details contains the list of downloads that it is completed. Similarly, if it's an upload, the trigger details will have a list of uploads which it has completed. So using that, you can now have control of the downloads which you had earlier started. Now you can do interesting post-processing work with the downloads. You want to access the file, or you want to send a server acknowledgement, you can do all those activities. Now, some important points to note that the background task which is launched it is a regular background task. It is not something special. It will be part of the pool of background tasks which are running in the system. So that it is subject to same CPU network quota, and it will be part of the pool. So it can be, if there are a lot of background tasks already running, there can be a slight delay before that task gets run. So we need to take note of that. And it also doesn't replace your foreground completion handler. Your foreground completion handler still can be run if the app is running. So this just gives an additional option for you to process your transfers right at the end of the transfer. So let's now quickly look at the demo of background transfer post processing. So here in this sample app, I have got 3 projects. As you can see, this is the background transfer UAP app, which is the foreground app. This one is my background transfer. This is a web service which is hosted in Azure. This is my own web service which I have written. What this web service does is it induces some failure in the download. So say you ask the web service to download 5 files from the web service, it will induce a random failure, and this is the background task to process the transfer. So if you look at so let me run the app. Okay, so in my background transfer, I start 10 downloads and add in a completion group. And what it does is it randomly fails and sends toast messages on how many have failed. But interestingly, as you can see, the downloads are getting failed, but they are automatically retried and getting succeeded. So ultimately, all the downloads are succeeded. So how do we do that? Is through this background task. So if you see in this background task, what we do is we actually get the failed downloads and then retry all the downloads in the background. So coming back to the presentation. So this is all about the background transfer, but in addition to that, we have done a lot of other improvements in other networking APIs, which are very popular, like windows.data.json. Now in this API, we had improved the debugging experience of this API in Visual Studio. Earlier, in a JSON object, there was no ability to see the individual members while debugging in the watch window. Now we have added support in the Visual Studio to get access to individual members of the JSON objects. We also have added a new API for easy serializing and deserializing of null values. Now that will help developers to process null values much faster and easier. The second thing what we have done in network background transfer API is that we have added improved support for removable media card downloads or SD card downloads. What happens is that we have made the API intelligent enough to detect that the download is happening on a removable media and then move the temporary files to the destination location so that the download is faster and completes quicker. We have done some more improvements in the Sockets API. One of the key improvement which we have done is now at the Socket API level, you can indicate a client certificate for authentication of the socket. This was a huge developer ask, and we have added it into our API. So in the Stream socket, you can now set a client certificate for authentication. Also, we have added support for port sharing in the Datagram socket, which is also a very powerful feature. So with that, we would appreciate your feedback and requests for new features on the networking API side. You can send that through comments on this Channel 9 video, or you can log your ideas in wpdev.uservoice.com. Also, you can voice your feedback and your request for new feature in the Windows Insider program. With that, we are done for today. Goodbye.